Hello, this is the solutions to Unit 1 practice exam for Math 1050. I include this reflection page at the beginning of every practice test as a chance for you, after you have corrected the practice test, to have some time to seriously reflect. I can't stress how important and how effective it can be to self-reflect on your learning, and not just how you feel your score is. It's not just about a score, it's how are you performing on each of these individual learning targets. These are the same learning targets that you had on the unit tracker, the Unit 1 tracker. Um, this part is not for me to fill out. This would be for you to fill out. And I included on your Unit 1 tracker, what kind of behaviors or what it means to be below proficient or emerging proficient. And I also gave you a chance on that Unit 1 tracker to make the same kind of self-reflections. But if you finish question 1, for example, um, understood the concept and answered with no assistance, or you needed help, or you really didn't have any idea, so you would mark here, all right, question 1, I had no idea um, anything about that one. Well, question 1 is tied to this objective here, learning target 2.1.3, means from section 2, or chapter 2 rather, section 1. Learning target 3, which was I can evaluate the difference quotient. Okay, well, maybe I'm below proficient, but you can go back to your unit tracker, figure out what some of the homework questions were that matched that learning target, and see if you finished that learning target. If you did the homework, you can also look at the unit review. There were some questions relating to this learning target. If that's still not enough practice, you can go to the math lab, ask them for some specific help on evaluating difference quotient. This just provides you a way to better target where your deficiencies are before going into the test, or also boost your confidence to show you where your strengths are. Rather than looking at the glass half empty, think glass half full sort of a thing. Is, you've mastered all these learning targets, you may have one or two you need to look at, but this isn't a requirement to do this page, but I think it's really helpful to self-reflect before going into any exam on how well you know each individual learning target. That can also give you a better idea of how you're going to perform going into the test. Knowing that you know these learning targets can help boost your confidence and give you a better testing experience. All right, question 1 of the Unit 1 practice exam. This comes from section 2.1. It's evaluating the difference quotient of a function. Remember, the difference quotient really is just the slope of a straight line. Yeah, that's all we're calculating here. First thing we'd want to do is figure out this first piece, f of x plus h. So f of x plus h, what we can do at this point, what I suggested is rewriting the entire function, but instead of x's, you make open parentheses where the x's were. So parenthesis squared plus 2 parenthesis plus 4, and then those empty parentheses are just filled with x plus h. And then we simplify, we expand x plus h squared, which is just x plus h times x plus h. And then we can distribute this 2 here to be 2x plus 2h plus 4. If we multiply these together, we get x squared plus 2xh plus h squared. So when we are ready to evaluate now, this expression, f of x plus h, is replaced with this expression here. So rather than writing f of x plus h, we can write x squared plus 2xh plus h squared plus 2x plus 2h plus 4. Now it says here we're supposed to subtract f of h. So when we're subtracting an entire function, we need to subtract the entire function in this case in a parenthesis, and then that's divided by h. Now the parentheses there is important because that reminds us that we're distributing that minus sign to all three terms. So that's really negative x squared minus 2h minus 4. And then the negative x squared then would cancel with the x squared. This negative 2h cancels with this positive 2h, and this becomes a negative 4 here, which would cancel with that positive 4. So the only terms left in the numerator are terms that have a factor of h. So 2xh plus h squared plus 2h divided by h. And the reason that's important that all of these terms have a factor of h in common is that can be factored out, leaving 2x plus h plus 2 divided by h, and now the h that we factored out can cancel with the h in the denominator, leaving what would be our final answer, 2x plus h plus 2. Okay, excuse me. Now question 2 is also from section 2.1, parts A and part B, finding the domain of a function. This is a pretty important topic in Unit 1. We'll see this coming up in several different chapters later on. Here we're finding the domain just based off of the equation of the function. With rational functions, rational meaning it's in the form of a fraction, rational function, where we're looking at is in the denominator, and it's going to be much more useful to us if we're looking at the denominator in factored form. And the reason that we focus here on rational functions and domain is we can't divide by 0. Dividing by 0 gives us undefined expressions. So x in this case cannot equal 2. If I plugged in a 2 right here, I'd get 2 subtract 2, which is 0. Likewise, x cannot equal 3. For the same reason, if I plugged in a 3 for this x right here, I get 3 subtract 3, which is 0. And then 0 times anything is 0. With the exclusion of those two x values, x can be any real number. So the domain of this function is any real number except for x equals 2 and x equals 3. And the preferred way of writing domain for 1050 is in interval notation. One thing I suggested in class, if you have a domain with 1 or 2 or a few excluded values, sometimes it's nice to be able to visualize those excluded values on a number line. So excluded I'm going to put as an open circle. So those are outside of the domain. Everything else I'm going to fill in that would be inside of the domain. So this interval here is negative infinity to 2, and then this interval here is between 2 and 3, and this interval here is from 3 to infinity. So those would be the intervals that comprise the domain, negative infinity to 2, and then 2 to 3, and then 3 to infinity. Part B is similar in that it is also a rational function. So we look at the denominator. It doesn't need to be factored, so we can easily tell the excluded value is x cannot equal 2. Normally in rational functions, the numerator plays no part in the domain because you can have 0 in the numerator of a fraction, just not in the denominator. However, this one's unique in that the numerator also has a square root expression. And if you recall, square root expressions have restricted domains where the expression underneath, in this case 2x minus 1, the expression underneath the square root always must be greater than or equal to 0. So not only can x not equal 2, we also need to see what values of x make this inequality true. So if I add 1 to both sides, I get 2x is greater than or equal to 1. Then if I divide by 2, I get x is greater than or equal to 1/2. So there's two restrictions acting on x. X needs to be greater than or equal to 1/2, but x cannot equal 2. Again, if we want to visualize this on a number line, the excluded value of 2 I'm going to represent with an open circle. And then starting the domain at 1/2, I'm going to put a bracket because it includes 1/2. We're going to shade here to the right because it needs to be greater than. So everything to the right of 1/2 is shaded except for x equals 2. So that tells us what the interval is going to be. 1/2 to 2. No, need a comma. Here we go. 1/2 to 2, and then 2 to infinity. So those would what I would consider to be important topics to study from Chapter 2, Section 1, would be finding the difference quotient from question 1 and evaluating the domain or finding the domain of functions in question 2, Part A and Part B. Question 3 is a question that comes from Section 2.2, graphing a piecewise function. What I suggested here is that for each piece of the piecewise function, make a table of a small xy table of values. And this statement for this piece tells us that x has to be less than -2. So I'm always going to start where it has a boundary switch. So it switches at -2 here. So I'm going to have x equal -2. And then less than that would be -3, -4. And then to find the corresponding y values, you plug your x values into here to find your y values. So if x is -2, -2 plus 2 is 0. If x is -3 right here, -3 plus 2 is -1. And then if x is -4, -4 plus 2 is -2. So I can plot those points. And notice it says x is strictly less than and not less than or equal to. So that means at this point right here, that's an open circle because there's no equal to part of this inequality. So at -2, 0, place an open circle, and then -3, -1, and then -4, -2. And the graph has to point in that direction because these are the values that are less, these values here are less than -2. Now for the middle piece, an xy table of values, my x values are between -2 and +1. So I can do -2, -1, 0, and 1. Those are the values that it says to use for x. And then to find y, you plug them in here, but there's no x value, there's no x variable to plug in. This is telling you that the y value is always going to be -3, regardless of the value of x. And because both of these are equal to inequalities, those endpoints are going to be open circles. Sorry, closed circles rather, because they're equal to, these are closed circles. So -2, -3, and then -1, -3, 0, -3, and 1, -3. That just forms a straight line between -2 and +1. Now, this bottom piece says starting at 1 here, and then greater than 1. And then to find the y values, we use this piece, whatever the x value is squared. So 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16. And because this is just a greater than and not a greater than or equal to, this has to be an open circle at 1, 1, and then 2, 4, and then 3, 9, 4, 16 would be off the graph. So that's a portion of a parabola right there. This right here is the complete graph of the piecewise function. Some things to pay attention to, some common mistakes I've seen is having too many closed-in circles. For example, if that was a closed-in circle right there, then this function wouldn't pass the vertical line test, or this graph wouldn't pass the vertical line test, meaning it wouldn't be a function. So pay attention to that. These are still functions, so they have to pass the vertical line test. Okay, question 4 is from 2.3. There were several learning targets in 2.3, and question 4 covers all the learning targets, evaluating a function, finding domain and range, intervals of increase and decrease, and this is actually from section 2.8, a one-to-one function. And actually, there's one more, looks like it inadvertently was left off. There should be a part E on here, which is find all local extrema. That was meant to be included on this problem. So let's see, one-to-one from 2.8. Here we go. Part A, evaluate the function with an x value of 1. So find f of 1. Normally, to find f of 1, we would just plug 1 into the equation of the function. We don't have an equation, we have a graph. This is still an x value here. So really what it's saying is if we were to make a table of values with an x value of 1, what's the y value? That's what this question is asking. So here's when x equals 1. The y value there would be 3. So the answer to this is f of 1 is equal to 3. Excuse me, domain and range in part B. So the domain, remember, is the set of all possible x values. We have an x value here of -4, -4, 0. -5 is not in the domain because if I plug in or if I try to find a point on the graph that has an x value of 5, there are no points on the graph here that have x values of 5, so -5 is not in the domain. The domain starts here at -4, and then it includes all of these x values here. All of these x values to the right of -4 are in the domain because at 3, for example, there's a point here, 3, -3, or here 1, 3, or -1, -3. All of these points, all of those x values are in the domain because they have points on the graph. But it ends at 4. There are no x values beyond 4 that have points on the graph. So the domain is between 4 and -4. But you notice here at 4 it's an open circle. So 4 is actually not included in the domain, whereas -4 is. So the way you would write this, and be very careful that you write it correctly, including -4, so -4 to +4, not including +4 because of that open circle. We can find range using a similar way, but just along the y-axis. 4, for example, on the y-axis, there aren't any points on the graph that have a y value of 4, so 4 is not in the range. Same as -4, there aren't any values on the graph that would have a y value of -4, but 3, that seems to be the highest value on the y-axis that's in the range, and then here -3, that seems to be the lowest value. So our range is restricted to between -3 and +3, and I'm going to include those values because if we look here, 3, this is a point 1, 3, so obviously 3 is in the range because there's a point on the graph with a y value of 3, and the same thing here, this represents the point 3, -3, and so -3 is a y value that has a point on the graph, so we include those with brackets. Okay, part C, find intervals in which the function increases and decreases. And when we read a graph, we're reading at the graph as x values are increasing, so the graph goes from left to right. So looking this way along the graph, these points here have increasing y values, so this would be an increasing part of the graph. The y values are getting larger. Same thing here. These points along this part of the graph have increasing y values, so that's an increasing part of the graph. And then these points here have increasing y values as x increases. So all three of those pieces there represent increasing portions of the graph. So, and rather than stating that it increases from this point to this point, we only state the x values on which that occurs. So these x values, and then between these x values, and then between those x values. So the graph is increasing between -4 and -3 between these x values. Then it's also increasing between these x values, -1 and 1. And finally, it increases between these x values of 3 to 4. And then decreasing portions of the graph are portions of the graph where the y values are getting smaller, even though the x values are getting larger. So here the x values are still getting larger, but the y values are getting smaller. So this is a decreasing part of the graph. And same thing here, even though the x values are getting bigger, the y values are getting smaller, so this would be considered a decreasing portion of the graph. And again, rather than saying it decreases from a point to a point, it's only the x values in which that occurs. So between these x values of -3 and -1, and then between these x values of 1 and 3. Okay, part D is the function 1-to-1. Graphically, when we talked about functions being 1-to-1, this was from section 2.8, had to pass a horizontal line test. So this graph fails the horizontal line test. This function is not 1-to-1. And you will need to justify, is the function 1-to-1? Why or why not? No, fails the horizontal line test. Now part E, finding the local extrema. That means find all the local maximums and the local minimum. And there might be one of each or more than one of each. A local maximum, for example, occurs here and here. In this portion of the graph, that's the highest point, and in this portion of the graph, that's the highest point. So those are both local maximums. So there's a local maximum at the point -3, 3, and at the point 3 or 1, 3. And then local minimum values. Here's a local minimum value, and there's another local minimum value. So we have a local minimum value at the point -1, -3, and at the point 3, -3. Okay, question 5. This is from section 2.6, transformations of functions. Also a lot of learning targets in this section. You need to be able to describe transformations when given an equation. You need to be able to build an equation when given a description of transformations. You need to be able to graph a function when given transformations. So there's lots happening in section 2.6. This one, question 5, is building or writing an equation when given some different transformations. So the parent function is the cube root of x. So we need to write a different function. I'm going to call g of x. So cube root of x, and then it's been shifted to the left 3 units. If it's moving left or right, a horizontal transformation occurs inside the function. So I'm going to put an x plus 3 inside the function, because anything that occurs inside the function moves the graph left or right. The graph moves up 2 units, since that's a vertical transformation that occurs outside the function, so that's going to go up 2 units. And then reflected across the x-axis, reflections are just negative signs. And since it's a vertical reflecting across the x-axis, that's vertical, that's going to occur outside the function. So if this is transformation number 1, this occurs right here. If this is transformation number 2, that occurs here. And then the reflection, if that's transformation number 3, that is represented by that minus sign right there. Okay. Sketch the following function using transformations. First thing to notice is what kind of function this is. This is an absolute value. Typically, absolute values, vertex starts at 0, and it's a V-shaped graph. So we've got to figure out what moves, what transforms. Is it skinnier? Is it wider? Is it reflected? So let's see. This moves down 1 unit. This moves left 2 units. This right here, the minus sign, is reflection on the x-axis. And then that 1/3, since it's outside the function, that's a vertical compression. So you can see there's a lot of things happening here. So first thing is to locate that vertex. Like I said, normally in these functions, the vertex is here at 0, 0, but it's been moved to the left 2 units, and then down 1 unit. So there's a vertex, and we know that it's going to be facing upside down rather than right side up because of this minus sign. Flips it upside down, that's reflecting over the x-axis. But also, that 1/3 in front is going to change the shape. It's going to make it a little steeper. So one thing you can do is, now that we know that the vertex is at the point -2, -1, we can make a table of values to find out a couple of other points just so we can have the correct steepness of the graph. So if I plug in -3, for example, for x, which would be a point right here, just on the other side of the vertex. If I plugged in -3 in for x right here, then -3 plus 2 is -1. The absolute value of -1 is 1. And then 1 times -1/3 is -1/3. Okay, -1/3 subtract 1 would be -4/3, or -1 1/3. So -3, comma -1 1/3, right there. And since this graph is symmetric, we know that a point gets reflected on the other side of the vertex. So those 3 points give us a pretty good look there of the shape of that absolute value graph. It's upside down. It's a little bit, it's compressed vertically because of that 1/3. And then it's been moved to the left 2 and down 1. Okay, question 7 is also a topic from section 2.6. Determine if the following function is even, odd, or neither. You would get no credit for just stating even or odd on this one and just guessing. You have to show how you know that it's even or odd or neither. And the only way to show that with the equation is to evaluate the function using the opposite of x. So in this case, we'd have 2 times the opposite of x cubed minus the opposite of x divided by 4 times the opposite of x squared. So looking at the denominator, -x squared is negative x times negative x. That's just positive x squared. So this is 4x squared. But here, the opposite of x cubed makes that term negative 2x cubed. And then subtract negative x there is plus positive. If we were to factor out that negative sign from the numerator, what we're left with is 2x cubed minus x all over 4x squared. And this expression here is what we started with. This is f of x, and it says we have the opposite of f of x. And so what we are left with then is this. We evaluated the function at negative x, and it resulted in the opposite of f of x as an indication of an odd function. And just as a way of reminder, if you evaluate the opposite of x and it results in the same exact thing that you started with, that would have been an even function. If neither one of these two things occur, if it's a mixture, some of it's the same, some of it's different, it's not all, then you would say that the function is neither even nor odd. Question 8 is from section 2.7, combining functions. These for A, B, C, and D were from learning target. The first learning target, which was adding, subtracting, multiplying, dividing. And then this one was the composition of functions. This was separate learning target. So for part A, we're just adding the f function to the g function. And all we're doing here then is combining like terms. So the 2x squared has no other like terms, but the negative 2x and the 5x can add to 3x. And then here the negative 5 and the positive 4 would add to negative 1. For part B, we have f of x. Well, it's f minus g of 2. So we can do this one of two ways. We can either find f of 2 and then subtract that from g of 2, or we can subtract f and g first and then plug 2 into that after it's subtracted. So 2x squared minus 2x minus 5, and then if we subtract 5x plus 4, that's going to result in 2x squared minus 7x minus 9. So this is f minus g. If we evaluate now this when x equals 2, then we would get 2 times 2 squared minus 7 times 2 minus 9. So here 2 squared is 4, 4 times 2 is 8, 8 minus 14 minus 9. 8 minus 14, that's negative 6 minus 9, it's negative 15. Now if we went back here and did it the other way where we did f of 2 minus g of 2, then if we plug 2 into here, we're going to get 2 squared, that's 4 times 2, that's 8, minus 4, minus 5, so that's negative 1. If we plugged in a 2 here, we'd get 10 plus 4, which is 14. So we get negative 15 either way. For part C, f times g We're going to use the distributive property. So 2x squared needs to multiply both terms. And then negative 2x multiplies both terms. And then the negative 5 multiplies both terms. And then we combine like terms. Okay, part D was f divided by g. And actually, again, the additions to this problem that you really should be prepared for if this were a test question is not only answer the question, but also find the domain of part A, C, and D. Anytime you evaluate a function at a value, like f minus g of 2 or g of f of 4, we're choosing the domain there to be 4, or in this case, we're choosing the domain to be 2, because that's the x value. But if you're evaluating a function just at x, we should be prepared to find the domain also. So going back to part A, 2x squared minus 3x minus 1 here, that's just a quadratic function. And we've talked about this. The domain of a quadratic function is negative infinity to infinity. Part B, we don't have to do domain because we were evaluating a function at a particular value there. Part C, there aren't any denominators that would make us be dividing by 0. There aren't any square roots or fourth roots or anything like that, any of those typical domain restriction functions that we've talked about. So the domain of this is all real numbers. Now for part D, however, the domain is going to have a restriction because right here in the denominator, we can't divide by 0. So what we need to figure out is what's going to make 5x plus 4, what's going to make it equal 0. And whatever that value is, we exclude it from the domain, we take it out. So if we were to solve this, negative 4/5 is what makes the denominator 0. So the domain is, I'm going to take this out. X cannot equal this value because I don't want 5x plus 4 to equal 0. So if the domain is everything excluding but not including negative 4/5, it's going to be negative infinity to negative 4/5 and then negative 4/5 to infinity. Now part E was g of f of 4. So the first thing we need to find is what is f of 4, because that's, when we're doing a composition like this, we're going to start with the innermost part, which is f of 4. So plugging a 4 in for all the x's into the f function is 2 times 4 squared minus 2 times 4 minus 5. So here 4 squared is 16. 16 times 2 is 32 minus 8 minus 5. 32 minus 8 would be 24. And then 24 subtract 5 is 19. So f of 4 is the same as 19. F of 4 and 19. So I can replace f of 4 then inside there with 19. So now I'm finding g of 19. So the g function is 5x plus 4, so this is 5 times 19 plus 4, and 5 times 19 is 95 plus 4, that's 99. Okay, question 9, this is from section 2.8. 2.8 introduced us to one-to-one functions. Remember, a function is one-to-one. A function that is one-to-one means that its inverse is also a function. In order to determine if a function is one-to-one, you look at its graph and it passes the horizontal line test, then it is one-to-one. We talked about how to find the inverse of a function here, which is what question 9 is asking about. In question 10, which we'll get to in a second, this is graphing the inverse of a function. So the things to remember about finding the inverse of a function, first thing is to switch the place of x and y, remembering that f of x is really just y. So if we switch the places of x and y, we have x equals y minus 1 divided by y minus 2. The second thing we do is to solve for y. So right now the problem is we have a fraction, we have a rational expression here, which we don't want to have when we're solving an equation. So I'm going to multiply both sides by the denominator. So now, and then also if we distribute there, we're going to have yx minus 2x equals, and then those cancel, so we have y minus 1. So solving this for y means we have to get all the y variables on the same side of the equation. So I can take and subtract this y over here. So yx minus y minus 2x equals negative 1. All I did is subtracted that y over there. But I only want to have terms that have a factor of y on that side. So I'm going to add the 2x and move it over here. So if I add the 2x over, I'm going to have yx minus y equals positive 2x minus 1. The reason I wanted all of those terms on the left side to have a y as one of its factors is because now that makes it a common factor for all those terms. So you can factor out the y on that left side. And then that solves the problem of having multiple y's because we factored out to a single y here. And now y is multiplying that x minus 1, so I can isolate y by dividing by x minus 1. And finally, we have y by itself. And this would be now the inverse of f. Now going back to read the directions, it also says to state the domain and range of both f of x and the inverse of f. Now going back to f of x, the domain of these functions we can find, in this case, since it's a rational function, we don't want to have a denominator of 0, so we can say that x cannot equal 2. We've practiced this a couple times already. It seems to be always that same value of 2. Anyway, the domain is negative infinity to 2, and then 2 to infinity. The range is not quite as easy to find when we just have the equation. It can be easy to find with the graph. We don't have the graph for this. So I'm going to skip range for a second. Go down here to the inverse. We notice that on the inverse we have a denominator here of x minus 1. So x cannot equal positive 1. So the domain is everything except positive 1. So negative 1 to infinity, or sorry, negative infinity to 1, and then 1 to infinity. Now, the reason I did the domain of each first, and we talked about this at some length, when we find the inverse, we switch the place of x and y. If I go back up to the original function, remember domain, these are your x values. So these are your x values for f of x. If we switch the place of x and y, that means in your inverse function, those become your y values or your range. So this right here becomes the range of the inverse. And then the reverse is true. These values represent the x values of the inverse, and if we switch the place, these x values would become the y values of your original function, so that becomes the range of your original function. So you can see the domain and range just switch from the original function f to the inverse of f. The range and domain switch because we switch the place of x and y. All right. Finally, on question 10, we got to sketch the graph of the inverse, and it's still the same technique. We're going to switch the place of x and y. So the original function f has the following points. So it has negative 5, 0. It's got 0, 5. Right here we've got 2, 1. And then here we've got 5, 2. So then to find the inverse, we just switch all the places of x and y. So instead of negative 5, 0, it's 0, negative 5. Instead of 0, 5, 5, 0, 1, 2, 2, 5. So 0, negative 5, 5, 0, 1, 2, and 2, 5. And one way to check if you've connected the dots the right way is that a function and its inverse, and I mentioned this briefly, I could have probably hit on it a little bit more, but a function and its inverse graph are a reflection across this line right here, y equals x. So as you compare the original function's graph to what we've graphed as the inverse, then we need to have a reflection across that line. It looks like we do. So those are some of the major topics you can expect on this Unit 1 exam. Once you've corrected your practice exam and looked at these answers, I would, like I said before, highly suggest you go through that reflection process. Look at the learning target that the question is asking about. For example, question number 10 is a learning target from section 2.8. Consider your mastery level of that learning target. Do you need to go back and do some more of the homework, or look at the unit review, look at your notes, maybe do some problems in the textbook that weren't necessarily assigned as homework but would give you extra practice, or go to the math lab and ask them specific help questions, not just I need help to prepare for a Unit 1 exam, I need help on how to find the inverse of a function or how to find the domain or whatever it is, but take some time to seriously reflect on your level of mastery of some of these learning targets so you can better prepare for the exam. Good luck.